So in the last class, we had discussed about improper integrals and how to evaluate those improper integrals. And in engineering applications, there are two important integrals in different areas of application and advanced mathematical applications. We come across these two integrals, beta integral and gamma integral. So how to evaluate them? We will now see this. So the first one is we'll discuss gamma. Sometimes they are discussed in a reverse order. But we will start discussing with gamma function. It's gamma function, not functions. Now, so this is called as the Euler's gamma function. Euler's gamma function with parameter alpha is defined as gamma of alpha. This is the capital gamma of the Greek letter. Gamma of alpha is integral 0 to infinity e power minus x into x to the power alpha minus 1 dx. Here, this is for alpha greater than 0. So this is the definition of gamma function. Now, so this integral frequently arises in, applications in science and physics, advanced physics. So now we can very clearly see that gamma function is an improper integral. Okay. This is an, so we have to discuss about the convergence of the gamma function. Now, gamma function is an improper integral for two reasons. It is an improper integral for two reasons. First one of the limits is going to infinity. All right. Upper limit. So one of the limits of integration is infinite. Second, sorry. Just a second, there's a disturbance. Yeah. Sorry. So one of the limits of the integration is infinite. And secondly, for alpha less than 1, alpha is greater than 0. So when alpha is less than 1, the power of x will be negative. So basically you will get 1 upon x power, x raised to the positive power. So for alpha lying between 0 and 1, what happens is at x equal to 0, the integrand has an infinite discontinuity. All right. The integrand has an infinite discontinuity. All right. So for these two reasons, it is an improper integral. However, it is convergent, and the gamma function convergence we will not discuss in this scenario. It is not the derivation or the proof of gamma function being convergent. We will not spend time on it, but in standard textbooks, the proof of gamma function being convergent, beta function being convergent, it is proved. So gamma function is convergent for all alpha greater than 0. It is convergent even for alpha lying between 0 and 1 and alpha greater than 1. So using this, so this we should know as a as a result, very important result. However, we don't have to pay much attention from the point of view of gate, where we have to do problem solving. We don't have to worry about how is it that it is convergent. Now, how to evaluate gamma function? So evaluation of the gamma integral. So let's integrate the integral by parts. So integrating by parts. So what's the gamma integral? Gamma function is integral 0 to infinity e power minus x to the power alpha minus 1 dx for alpha greater than 0. Now, this is algebraic, this is exponential. So which is the first function? The algebraic one will be the first function. So first function into integral of the second. Integral of e power minus x is e power minus x upon minus 1. That will be minus of e power minus x minus integral derivative of the first function, that is alpha minus 1. Okay, we can, all right, we can do it for this also. No problem. Okay. Alpha minus 1 into x to the power alpha minus 2 into minus e power minus x dx. So let us apply integral 0 to infinity. Infinity is you will have to apply limit. Now, x goes to infinity. This particular term, you see, x, this we evaluated earlier. As x tends to infinity, e power minus x. That means e to the power minus infinity. This goes to 0. This goes to 0 very fast, and then this term apparently is going to infinity, but this the product of this will be 0. All right, this goes to 0 and this also goes to 0, and we are left with minus plus minus. You take minus into minus plus, take alpha minus 1 outside, and then integral 0 to infinity. What do we have? X to the power alpha minus 1 into minus 1 into e power minus x dx. So if we observe with the original, you get alpha minus 1 times gamma of alpha minus 1. So this is an important result. Which commonly this equality is also written as gamma of alpha plus 1 will be alpha times gamma of alpha. So this just instead of taking gamma of alpha, if we take gamma of alpha plus 1 and do integration by parts, again we get to this particular result. Okay. So this is the way. So it is a reduction formula. And by reducing this, we can evaluate gamma function for various values. So now let us see that. The first one. So first result, gamma of m plus 1, where m is a natural number, is m factorial for all m belongings to natural numbers. Okay, that is gamma of m plus 1. Now next, now gamma of 1, let us find out how we can derive this. I will explain. Gamma of 1. So what is gamma function? Gamma of alpha is 0 to infinity e power minus x to the power alpha minus 1 dx, right? So when alpha is 1, we get this as integral 0 to infinity e power minus x into x to the power 1 minus 1, x to the power 0, that is 1. So we are left with this integral 0 to infinity e power minus x. And this integral is minus of e power minus x from 0 to infinity. Take minus sign outside. This goes to e raised to infinity becomes 0 minus e power 0 is 1. So therefore we get gamma of 1 is 1. Next, we'll apply this reduction formula. Gamma of 2 is gamma of 1 plus 1, which is, so alpha plus 1, so which is alpha into gamma of alpha. So 1 into gamma of 1. Gamma of 1 is 1 anyway. So you get 1. So gamma of 2 is also 1. Then next, gamma of 3. Gamma of 3 is gamma of 2 plus 1. So what will this be? It will be 2 into gamma of 2. So 2 times what is gamma of 2 is 1. So you get 2. What will be gamma of 4? So gamma of 3 plus 1, which is 3 times gamma of 3, which is 3 into 2, which is 6, which is 3 factorial. Because 3 into 2 is 3 factorial. Like this. So it will proceed like this. Gamma of 5 will be 4 plus 1. Gamma of 4 plus 1. That is 4 into gamma of 4. That is 4 into 3 factorial, which is 4 factorial. So on, you will get gamma of m is, gamma of m plus 1 is m factorial. Okay, where m is a natural number. So this is a very important result. related to gamma function. Now, how do we evaluate? There are examples, but we have to further find out about gamma function. But beta and gamma function are related. So there are certain values of gamma functions which we can find out using beta functions. So now let us go to beta integral. This is the basics of gamma function. Then we have the beta function. So now beta is a function of two variables. So generally sometimes these topics are discussed after discussing function of several variables. However, the results that are used are in functions of single variables, and I will discuss some questions that come in the gate based on these two functions. So that is the reason why I'm covering it right now. Now, the beta function with parameters L and M is defined as beta of L comma M is integral 0 to 1 x to the power L minus 1 and 1 minus x to the power M minus 1 dx. Here L is greater than 0, comma M is greater than 0. So this is the definition of the beta function. The integral, the limits are not infinite. It is in fact between 0 and 1, but it is a product of x raised to the power L minus 1 and 1 minus x raised to the power M minus 1. So now beta function is an improper integral for which values we from the gamma function we can understand. So beta function is an improper integral for L lying between 0 and 1 or M lying between 0 and 1 or both simultaneously or both. So either L lying between 0 and 1 or M lying between 0 and 1, and the discontinuities will be beta is an improper integral for L lying between 0 and 1 or M lying between 0 and 1 or both, because as at x equal to 0 or x equal to 1, the integrand has infinite discontinuity. Okay. So when x equal to 1, this goes to 0. And if you have a negative power, it goes to infinity. When x equal to 0 and L is less than 1, so something going to 0 with a negative power, this will go to infinity. So, all right. So, but beta function is also convergent. Although this is true, beta function is also a beta integral is also beta function or beta integral here is also convergent. Again, we will not discuss, the derivations are there, and from gate point of view, we don't need them. So that means they have a finite value. So now there are properties of beta function. There's a very simple property. We can check this. Beta of L comma M will be same as beta of M comma L. That means they are symmetric with respect to their two variables. We can prove this. You can check this proof by substituting x as 1 minus t in any of the in the first integral and evaluate it. You will get it will get reorganized, and you will get beta of M comma L. We can do this, no problem. Then another form of beta integral. This is very important. This is extremely important. So now we have, what is beta function? Beta of L comma M is integral 0 to 1 x to the power L minus 1 minus x to the power M minus 1 dx. Okay, substitute x is equal to sine square theta. Therefore, dx will be 2 sine theta cos theta d theta. Okay, and let's look at the limits. And 1 minus x will be 1 minus sine square theta, which is cos square theta. So this is x and this is theta. All right. So for x equal to, when x is 0, sine theta will also be 0. Theta will vary from 0 when x equal to 1. And we are talking about these limits for L minus 1 greater than 0. So take only the positive values of theta. So when x equal to 1, sine theta value will be 1. So theta will be pi by 2. So when x is equal to 1, theta is pi by 2. So this beta integral, beta L comma M, is converted to integral 0 to pi by 2. This is sine square theta times L minus 1. And this is cos square theta times M minus 1 times dx becomes 2 sine theta cos theta d theta. So what do we get? Integral 0 to pi by 2, we get sine theta raised to the power 2L minus 2 cos theta raised to the power 2M minus 2 times 2 sine theta cos theta. Now you take the product. Now product sine theta multiplied by this, we will get twice of sine 2L minus 1 times theta cos of 2M minus 1 theta. So this is another form of beta integral. So sometimes beta integral is not just in terms of x and 1 minus x, raised to the power L minus 1 m minus 1. This beta integral is another form of beta integral. So the above is another form of the beta function or the beta integral. Okay. So sometimes question is given like this, strange, and we don't know how to solve. Of course, if L and M, we know this particular integral, we can use Wallis formula to solve. If L and M are integers, very easy, positive integers especially, then we can use Wallis formula to find out the result. So that is easy. However, sometimes we have to convert this to another form. Now, there is the third very important point. The third very important property is the relation between beta and gamma function. So, beta function is defined like this: beta of L comma M is gamma of L into gamma of M by gamma of L plus M, L plus M. Actually, this relation is the proof of the Wallis formula. When L and M are integers, we know this. If L and M are integers, this will be factorials, and this will also be factorials. And we know the Wallis formula. Wallis formula actually is derived from this relationship between beta and gamma function. And I will go through this because this integral, meaning not the proof part of it, but this has a use. This relationship has a use, and we get problems directly based on the result coming from this formula. We'll see in at least 3 years papers, we got a problem which appears to be a simple integral, and it appears, but it uses the beta and gamma functions. So I'll not go through the proof. Proof will involve, some substitutions and a change of coordinates into polar coordinates. You can look into, if you are interested, look into the proof of this in any of the standard textbooks. But I'll use this relation to find this value. Okay, fine. Evaluation of this is a very important result. Gamma to the power, gamma of half. Okay. So gamma to the half. So if you want to do gamma to the half, gamma of half, you can take L and M to be half. So let L equal to 1 by 2, M equal to 1 by 2. Then what happens? Beta of half comma half will be equal to gamma of half into gamma of half by gamma of 1. And we know gamma of 1 is 1. So we get gamma of half whole square is beta of half comma half. So gamma of half will be under root of beta of half comma half from this. Okay. So now beta of half comma half, what will that be? Use this formula. Don't use x into 1 minus x formula. Use this one. That will be a little difficult to solve. You can try integrating the beta function by the usual substitutions. You will find it very difficult. Use this result. Okay, this particular result. So substitute L equal to half, M equal to half. So 2 into half becomes 1, 1 minus 1, 0. So this is 2 times integral 0 to pi by 2 sine to the power 2 into half minus 1 theta cos to the power 2 into half minus 1 theta d theta. So sine power 0, cos power 0, you will get twice of 0 to pi by 2 d theta, 1 d theta. That is 2 times of theta. Integrating 1 with respect to theta gives theta. So you'll get 2 times pi by 2 minus 0, which is pi. So beta half comma half is pi. Therefore, gamma of half is under root of beta of half comma half, which is under root pi. So gamma of half is under root pi. So gamma, it's a very important result, this one. Three times this question has come. And this has a bearing with the error function and probability analysis of random variables, continuous random variables. So we will look into those things later as an error function. So now further extensions of this. So if gamma of half is under root pi, what will be gamma of minus half? Then we will have to call for this result. So from this, because we know gamma of half, so what should we substitute to find gamma of minus half? What should we substitute alpha as? Should we substitute alpha as plus half or minus half? So clearly we should substitute alpha as minus half. So this will give us gamma of half is equal to minus half into gamma of minus half. Now gamma of half is root pi. So gamma of minus half is minus 2 times root pi. So this is another result, but gamma of half is most often used. And then gamma of 1 by 3, we can 3 by 2, we can find out. So this is one result. Next result is gamma of 3 by 2 will be gamma of half plus 1, which is gamma of alpha plus 1 is alpha times gamma of alpha. So this is half into gamma of half, which is root pi. So it is root pi upon 2. Okay. So similarly, we can find out gamma of 5 pi by 2 and so on. So these are the results. So this is sufficient from any gate or even IES entrance point of view. Unless we want to go into deep mathematical examinations, this is sufficient. perfectly sufficient for what we have done. So gamma function, what I'm just reviewing, gamma function, uh, gamma function is defined as 0 to infinity e power minus x, x to the power alpha minus 1 dx for alpha greater than 0. Although it's an improper integral for two reasons. It is a convergent function, and to evaluate gamma integral, we use the reduction formula by integration by parts. We get this result, gamma of alpha plus 1 is equal to alpha into gamma of alpha. So we get a result, gamma of m plus 1. If m is an integer, that means if alpha is an integer here, we'll get alpha factorial. So gamma of m plus 1 is equal to m factorial for m being a positive integer, natural number. Gamma of 1 is 1, gamma of 2 is 1, gamma of 3 is 2 factorial, gamma of 4 is 3 factorial, gamma of 5 is 4 factorial, so on. And beta function is defined as L comma m. Beta of L comma m is integral 0 to 1 x to the power L minus 1 into 1 minus x to the power m minus 1 dx. It's also a convergent function. Some properties, beta of L comma m is same as beta of m comma L. Another form of beta integral is this, beta of L comma m is 2 into integral 0 to pi by 2 sine of 2 sine theta raised to the power 2L minus 1 cos theta raised to the power 2m minus 1. Now relationship between beta and gamma functions are these. Beta of L comma m is gamma of L into gamma of m upon gamma of L plus m. So if we actually evaluate this, you will get the result of Wallis formula that you can take steps to derive from this. So then we found gamma of half is under root pi, gamma of minus half is minus 2 root pi, gamma of 3 by 2 is root pi by 2, and so on. Now, how to find gamma of 4, 1 by 4, gamma of 3 by 4? That usually is not asked, but there is a result. Of course, for that, we'll have to do analysis of complex functions and then we derive a result. In future, we will derive, but I'll just present the result here. Euler's reflection formula. There's a formula, gamma of x into gamma of 1 minus x is pi upon sine of pi x. So from here, by suitable substitutions, x as 1 by 4, you get gamma of 1 by 4 into gamma of 3 by 4 is 2 root pi, and then reverse gamma of 3 by 4 into gamma of 1 by 4. So with certain manipulations, we can find gamma of 1 by 4 and gamma of 3 by 4. So that's not required for us. This much knowledge is sufficient. Now we'll do some problems that have appeared in the GATE exam based on this. First one, evaluate integral 0 to infinity e power minus y cube into y to the power half dy. Okay, of course, this question was a multiple choice question. It is not a not a evaluation numerical question. It can be a numerical question also, but this was a multiple choice question in one of the GATE papers. Now, when we apparently see this, we don't see immediately, we cannot recognize that what kind of integral it is. And we struggle. If you try to do integration by parts, we will struggle with this. It's a reduction formula, but we'll straight away we're not recognizing it. And you can do it as a homework exercise. Try to integrate this integral by parts. You will have a very tough time. Now, let us do how to solve this. So let us use a substitution. What I want, whenever I get e power minus something, easiest is remember the gamma function. Gamma of alpha is integral 0 to infinity. So this is matching e power minus x into x to the power alpha minus 1 dx. This is the gamma function. Now let us see, can we reduce this to this form? For that, what should we do? We have to replace y cube by another variable, either t or x. So we'll replace by x. Let us see. Substitute y cube. Suppose it was x cube, then substitute x cube by t. Per here, it is y cube. So substitute y cube as x. So then we get 3y square dy. 3y square dy is dx. Now I want dy. Let us see. Now dy is 1 upon 3 by 1 upon y square dx. Now what is y? Is cube root x. So dy will be 1 by 3 into y to the power, x to the power 2 by 3. I'm replacing y by x to the power 1 by 3 whole square. So I get x to the power 2 by 3 dx. Okay. So now let us substitute. Therefore, the integral will be, now we have to look at the limits also. X, y and x. We are converting from y to x, the variable y to x. So when y is 0, this is our substitution. So x is also 0 and it's a continuous function. It's a polynomial continuous function. And when y goes to infinity, x also goes to infinity. So that doesn't change. So I remains integral 0 to infinity e power minus x. Now y is x to the power 1 by 3. So x to the power 1 by 3 into half. X to the power 1 by 3 raised to the power half is x to the power 1 by 3 multiplied by 1 by 2. So x to the power 1 by 6 into dy will be 1 by 3 by x to the power 2 by 3 dx. So this is 1 upon 3 times integral 0 to infinity e power minus x. And what do we get? 1 by 6 x to the power x raised to the power 1 by 6 minus 2 by 3. It is minus 1 minus 4 upon 6, which is minus half. This is a very important result. Look at the pattern of the integral. E power minus x, x to the power minus half. So I will write this as e power minus x, x to the power half minus 1 dx. Now you look at this integral 0 to infinity e power minus x to the power alpha minus 1, correct? E bar minus x to the power alpha minus 1. What is this? What is this? It is gamma of half. This integral is gamma of half. So this integral value is under root pi upon 3. Okay. This integral value is under root pi upon 3. Note, this part is, when you get an integral like this, immediately you can convert. So gamma function is useful to evaluate integral like this. Okay. Next question. Is it clear? Have you copied down? No answer. Should I give time for you to write down or should I go forward?
Yes, sir. Go forward.
Okay. Look at this next integral. Second example. Evaluate I is equal to 1 by root of 2 pi integral 0 to infinity e power minus x square by 8 dx. This is your error function that is used in probability distributions. This is one of the forms of the error functions, some transformation. But that error function is related to gamma function. So generally, like indefinite integrals, some integrals you cannot evaluate in indefinite integrals. Like e power x square or e power minus x square. So far, with advancement of mathematics, the indefinite integral as a function, we have not found an indefinite integral for these integrals. These are indeterminate integrals as an indefinite integral. So we find that by the methods, the regular methods of indefinite integrals, we cannot find them. We can't evaluate them. We can't find an antiderivative. We have to use, if it's a definite integral, we have to use numerical methods like the Simpson's rule or trapezoidal rule or any other numerical methods of integration. However, if limits of integral is from 0 to infinity, we can evaluate this using gamma function. So, but we should know that indefinite integrals or the antiderivative functions for e bar x square and e bar minus x square do not exist. So that's a side point. Now coming to the main point here. Now, because I have seen 0 to infinity and I'm seeing e power minus x square by 8. So my thought would be to substitute x square by 8 as t. Okay. So then we take the positive because x is lying between 0 to infinity, x is positive. So take the positive root. X will be under root 8, that is 2 root 2 times root t. So dx will be 2 root 2 into derivative of under root t is 1 upon 2 under root t dt. So we have dx as root 2 upon root t dt. Okay. Now let us substitute. So there's a side point. Now let us see the limits. X is varying from 0 to infinity, and t is a continuous function, like because it is x square upon 8. It is a algebraic polynomial. It's a continuous function. So when x is 0, t is 0. And when x is infinite, is approaching infinity, t also approaches infinity. So this integral will be 1 upon under root 2 pi, integral 0 to infinity. I get e power minus t into dx is root 2 upon root t dt. So I take this root 2 outside, I get under root. When I bring this root 2 outside the integral, it cancels with the under root 2 in the denominator. So I'm left with 1 by under root pi, integral 0 to infinity, e power minus t, t power half, t power minus half. So we have seen this integral just there in the previous problem here. That's why I said that particular integral is important. So from there, we can deduce 1 by under root pi, integral 0 to infinity, e power minus t, t to the power half minus 1 dt. Okay. So this is what? What function is this? Gamma of half I 1 upon root pi into gamma of half. So that is what is I. And gamma of half we know is under root pi. So this is 1. So the value of this integral is 1. Got it? So next one I'll give you. You please solve and give an answer to me. Evaluate I is 1 upon 2 root pi integral minus infinity to infinity e power minus x square upon 2 dx. Okay, I'll give you a few minutes time, maybe 3 to 4 minutes time. Please solve and get me the answer for this integral. Yes, you can put it in the chat, your answers. Good. Answer is correct. One answer. Good. Two answers. I'll give 3 minutes time. So let us look at this. First of all, it is minus a to a of e power x square upon 2 with a minus sign here. E raised to the power minus x square upon 2. So this is an even function. E power minus x square upon 2 is an even function. So we can write this as 1 upon under root 2 pi into twice of integral 0 to infinity e power minus x square upon 2 dx. So we'll be getting under root 2 by pi into this integral. Now we need to evaluate this. So substitute x square upon 2 is equal to t. So which implies x is under root 2 into under root t, which implies dx is under root 2 into 1 upon 2 under root t dt. Okay. So I is under root 2 upon pi. Now again, as x is 0, t will be 0 when x goes to infinity, t goes to infinity. So integral 0 to infinity, we get e power minus t into 1 upon 2 under root t dt. No, multiplied by root 2, I'm sorry. Root 2 times 1 upon 2 root t. So now this we get as under root 2 by pi. You take this out, 1 by under root 2 integral 0 to infinity e power minus t, t to the power minus half dt. So this will be under root 2 cancel. You are left with 1 upon under root pi integral 0 to infinity e power minus t into t to the power half minus 1 dt. This is 1 upon under root pi gamma of half. So 1 upon under root pi times root pi, which is 1. So this is the result. So all the 3 questions that I've discussed today, all the three questions are previous year's GATE questions from previous year's GATE papers. So that is why it was important to cover, because at least in a span of 10 years, at least 3 times this questions has come. So this much is sufficient for us. We don't have to go very in depth with other functions associated with gamma and beta functions. So with this, we complete this improper integral section. Now comes a very important section, that is areas under curves or applications of integrals. So I'll just start sharing. Just a second. I'm just setting up a new page. Yeah. So application of integrals, and in what I've shared to you in notes. So we have completed functions, limits, continuity, differentiability, differentiation, application of derivatives, indefinite, definite, and here we go to application of integrals. Okay, these are all calculus of functions of single variable. There's multiple integrals. We will come to multiple integrals after we have a discussion on functions of several variables. But in this part, in function of single variables, integrals are used for finding length of plane curves, that is called as rectification, that is length of plane curves, then area bounded by plane curves, and volumes and surface areas of solids of revolutions. So these three applications, and they are very, very useful in various problems on physics and engineering. So this is one of the reason why integrals we use, and we use differential equations, and to integrate to solve the differential equations we have to do integration. So we use these two very, very often. Now, before we start areas and the curves, very, very important topic is how to draw curves. And these, what I'm discussing now, is something very, very important. Okay. Curve tracing. Generally, if we are very good at tracing curves, we'll have a very quick idea of how to solve a problem. So you know that we just have 3 minutes time maximum per question to solve in a paper. So if we have an idea of curve tracing, then that will help us very fast in thinking, and we can draw graphs very, very quickly. Okay. So first aspect of tracing a curve is its symmetry. So now sometimes the curves, they're not functions. We have to remember that curves may not be functions. So how to trace a curve? So we'll write, first of all, we will um, write equation of the function in this manner, or equation of the curve in this manner. So here, suppose we have this function y equal to f of x. We will write equation as f of x comma y, capital F of x comma y equal to 0. So for example, we have this equation of the ellipse. So ellipse by itself is not a function, but you can express y in terms of x and make it as a function. So we will write this expression as f of x comma y as x square upon a square plus y square upon b square minus 1 equal to 0. So that means we bring all the terms to one side of the equation and equate it to 0. So that is what is meant by writing the function in this form, the equation of the curve in this form, f of x comma y equal to 0. Okay. So now after that, after we do that, first thing we have to check is the symmetry of the curve. To draw the curve, we need to know the symmetry. Now the question is, these days we have such graphing tools. Okay, online graphing tools, you type the function, it will give the answer. But these graphing tools are based on this mathematical concepts, the programs. And for a exam like GATE and even IES, you don't have an opportunity to use graphing tools. So you need to know the various aspects of curve tracing. The number one is symmetry, symmetry of the curve. So symmetry about y-axis. When will the curve be symmetric about y-axis? So if the equation remains unaltered by replacing x by minus x, that means f of minus x comma y is equal to f of x comma y, then the curve will be symmetric about the y-axis. So we can look at this equation. We know this equation, x square equal to 4ay. I will take a as 1. I will just take x square equal to 4y. And we will trace out this particular curve. So this is your parabola. Y is equal to x square upon 4. That is the parabola. So here we can see that the curve is symmetric. So when we replace x by minus x and the equation does not change, that means it's an even function. So because it's an even function, it is symmetric about the y-axis. So this is one. Now symmetry about x-axis, same logic. If you replace y by minus y and the function remains unchanged, f of x comma minus y is equal to f of x comma y, then the function is symmetric, or the graph is symmetric about the y-axis, sorry, about the x-axis. So let us now see this. This is y square is equal to 4x. So let's look at the graph. There's the graph. Yeah. So there's a graph of y square equal to 4x. So function will be symmetric about the y-axis if at about y equal to 0, the sign does not change. So put y equal to 0, that's the x-axis. So about the x-axis, y square minus 4x is positive. About the y-axis, x square minus 4y is positive. Now symmetry about the origin. Okay. There is a difference between the point number 3 and point number 4. This is symmetry about both the axes. Symmetry about both the axes means both of this are simultaneously satisfied. Just a second. Just sorry. Okay. Yeah. So where were we? Symmetry about both the axes. Symmetry about both the axes means both these conditions hold true. Replacing x by minus x, function, the equation doesn't change. Replacing y by minus y, the equation doesn't change. So it is symmetric about y-axis and symmetric about x-axis respectively. However, symmetry about origin, when we talk about symmetry about origin, that we can conclude if x is replaced by minus x and y is replaced by minus y simultaneously. If we do that simultaneously, then it is symmetric about the origin. Now look at the examples here. This is the ellipse x square by a square. I will make it simple. I'll write x square upon 4 plus y square upon 1 is equal to 1. So this is an ellipse. Now it is symmetric about both x-axis and y-axis. We know that. I'm sorry. So this is an ellipse. We know that it is symmetric about x-axis and y-axis. So put y equal to, replace y by minus y, equation doesn't change. So it is symmetric about the x-axis. Replace x by minus x. The equation doesn't change because of the square. So it is symmetric about the y-axis. So same is applicable for even circle. X square plus y square is equal to a square. So it is symmetric about both x and y axis. Now look at this. These are individually not symmetric about any axis. Y equal to x cube and xy is equal to c square. So y equal to x cube, this graph we have visited so many times. So although these are something very simple graphs, but sometimes we get difficult functions for which curve tracings will help. So now this is neither symmetric about x-axis nor symmetric about y-axis, because look here. Now I will write f of x comma y as x cube minus y equal to 0. Now I replace x by minus x. I get minus x cube minus y, which is not equal to f of x comma y. And f of x comma minus y, I replace y by minus y. I get x cube plus y, which is not equal to f of x comma y. So it is neither symmetric about the y-axis nor symmetric about the x-axis. However, if I replace both x and y simultaneously by their negatives, okay, what I get minus x cube plus y, which will be minus of f of x comma y. Such a function is symmetric about the origin. It is like an odd function. F of minus x is equal to minus x. Sorry, f of minus x is equal to minus of f of x. So this one will be symmetric about the origin. So that is the result. Or here in the equation, what it's said is if I replace x and y, in the equation, if x and y are on the either side like that, what happens is f of I replace x by minus x and y by minus y, the minus minus sign cancels. So the equation remains same. So that is why this is said like this. And for this example also, the hyperbola, this is a rectangular hyperbola. You can see here x, y equal to 4. This is a rectangular hyperbola. So it looks like this. So again, it is symmetric about the origin. When we say symmetric about the origin, what does it mean? You take any line passing through the origin. So any chord of the curve passing through the origin. Just a second. So symmetry means this is the chord, this point and this point. This chord will be bisected at the origin for every point in the curve. So there will be 2 points coming into, you draw any line that will cut the curve into 2 points. And if that line is passing through the origin will be the midpoint. That is the symmetric nature across the origin. Okay. All right. Symmetry. So here we can see for this case, I replace f of minus x comma minus y. If I do, it will be minus x into minus y minus 4. I get xy minus 4, which is same as the original function. Okay. So this is symmetry about the origin. Now symmetry about the line y equal to x. If x is replaced by y and y is replaced by x and the function doesn't change or the equation doesn't change, then we have that the graph will be symmetric about the line y equal to x. Why is it necessary? This one, sometimes we have to find area between a curve and the line y equal to x. That time, if we consider symmetry, it will be very, very useful. So let us plot some curves. So this we know anyway, x square plus y square equal to 1. We can plot this one. X cube plus y cube is equal to 3axy. So I will write x cube plus y cube is equal to 3xy. Okay, OneNote cannot evaluate this graph. These graphs have specific names, as I'll discuss later, but this one, if we replace x by y and y by x, they remain the same. The equation remains the same. So I'm trying to input. I hope. Okay, I'll put 6xy. Six xy. So instead of 3xy, I think 3xy has certain issues. I think it will not be solvable. It is 3xy is also working. So this is the graph. I'm just talking about symmetry part, but I will also talk about how to trace this curve later. But right now I'm talking about the symmetry part. Just a second. So we have to show that this line is symmetric about the line y equal to x. So you see y equal to x. I'll change the color of y equal to x. Okay. Yeah, so this is the graph. So this red line is y equal to x. So we can see the symmetry of this curve. So sometimes question comes, find the area bounded by the loop of this curve. Okay. So for that, if the curve is given, then we should know how do you find the this will very much help that this the line y equal to x is symmetric. This knowledge of the symmetry of line y equal to x will very much help, because if we can find the area bounded here multiplied with 2, we will find the total area. So that is why these things are important. So that is symmetry about the line y equal to x. Then the next result, let's go up. Symmetry about the line y equal to minus x. So here in the previous case, we replaced x by y and y by x. But if we replace x by minus y and y by minus x, and the function doesn't get altered, then we say that it is symmetric about the line y equal to minus x. So this previous graph is not symmetric about the line y equal to minus x, or x plus y equal to 0. All right, ellipse is not symmetric that way, but circles are symmetric. And there's an equation of another circle, which gives, if we replace y by minus x and x by minus y, the equation, the circle doesn't get altered. The circle remains symmetric with respect to the line y equal to minus x. So these are some points on symmetry. Next, how do we find whether curve passes through origin or not? And what will be the tangents at origin? Curve passing through origin is very simple. Just a second. So curve passing through origin, very, very simple. Zero comma zero should satisfy the equation of the curve. That's all. So it passes through origin. So here we see the same thing. 0 comma 0, like x cube plus y cube equal to 3xy. 0 comma 0 passes through. 0 comma 0 satisfies this equation. So it passes through origin. Now I want to find out the tangents at origin. To find the tangents at origin, the trick is this. Equate to 0 the lowest degree terms occurring in the equation of the curve, because it is going to 0 comma 0 is satisfying, so there is no constant term in the equation. So the lowest degree term will be degree 1 terms. So when you take the degree 1 term, so here in this equation, x cube plus y cube plus 3xy. So the degree of the first term here, the degree is 3 x cube. This is of the third degree. Y cube, it is of third degree. X into y, it is degree 1 into degree 1. So that is a power m and a power n. It is a power m plus n. So we just add the degrees. So together, this is a degree 2. This is of degree 2. So the lowest degree term in this equation is degree 2. So equate that to 0. So we equate 3xy to 0, 3axy, and a is a constant. So we get x equal to 0, that is the y-axis, and y equal to 0, that is the x-axis. These are the tangents to the curve. So take the lowest degree term and equate that to 0. And whatever you get, even if you get a linear equation equal to 0, then that will be the tangents to the curve. So here we have two tangents, which we can observe here to this curve. X-axis is a tangent, y-axis is a tangent. So these are some rules which are not just tricks, but if you know these rules, it is very, very helpful. Now, point of intersection of the curves with x-axis and y-axis, this we all know. How to find points of intersection of the curves with x-axis and with the y-axis. It's not difficult. We have been doing this in, in several basic mathematics courses. I should just leave it here. Okay. So when you put y equal to 0 and solve for all real values of x in the equation of the function, then we get the points where the curve cuts the x-axis. For example, I want to find x square by 4 plus y square by 9 equal to 1. This is an ellipse. I want to find where does it cut the x-axis. So put y equal to 0. So I get x square by 4 equal to 1. So from there I get that x square equal to 4 and x will be equal to plus or minus under root 4. So it will be plus or minus 2. So it will cut the x-axis at minus 2 comma 0 and 2 comma 0. Okay. Now, if I want to find out where it cuts the y-axis, so I have to put y-axis has x coordinate 0. So put x equal to 0. Then we are left with y square by 9 equal to 1, which means y square is equal to 9 and y will be plus or minus root 9, which is 3. So the curve cuts the y-axis at 0, 3, 0, minus 3 and 0, 3 at 2 points. So this is for any function, this is the way to find points of intersection of the curve with the x-axis. Now, sometimes the curves are a little tricky. We have to know where does the curve lie and where does the curve not lie. Some simple common sense so that we don't make mistakes in drawing the curves. Okay, the region where the curve does not lie, that is easy to find. More better than where does the curve lie. Now, if the values of y is imaginary for certain values of x, then the curve does not exist in those regions of x. Very logical. And similarly, vice versa. If the values of x is imaginary for certain values of y, then the curve does not exist in those regions of y. So here, two examples are given. Y square is equal to 2x. So when x is negative, y is not defined. So curve exists. So this is y square equal to 4x form. It's like a parabola, like the one we see here. So y square equal to 4x. This is an example. So when x is greater than 0, y exists. And there are two values of y that exist for any value of x greater than 0. But if x is negative, y is not defined. So curve does not exist on the negative side of x-axis. So that's how we determine that that's how we determine. So here this is the example, y square equal to 4, and we need to know to plot the graphs by hand. It's not just by graphers. So there's y square equal to 4x. So it does not exist in this region, the negative side of x-axis. Similarly, this one. This is a good curve. Y square into 2ax is equal to x cube. So this is x cube upon 2a minus x. So clearly, two things we can observe. When x approaches close to 2a, all right, this goes to infinity. Second is when x approaches 0, this goes to 0, no problem. Next part is the product. This right hand side has to be positive because the left hand side is a perfect square. So left hand side will always be positive for any value of y. So right hand side also has to be positive. So for the curve to exist, curve to be defined, x cube by 2a minus x must be greater than 0. So I will write this like this. Just see the way I'm writing. I'll write this as x square multiplied by x. Okay. And I'll multiply and divide by 2a minus x. So I'll get 2a minus x the whole square. So I'm dealing with inequalities. I'm not dealing with equalities. So what it means is that the product of all these terms is positive. This is the inequality. So I need not consider the perfect squares, x by 2a minus x whole square. Whether it is positive or negative, it will not affect my inequality. So in terms of sign, so x this equivalent to x into 2a minus x is greater than 0, which implies, from wavy curve method or, the quadratic, I don't want x to be having a negative coefficient. I multiply throughout with -1. I get x times x minus 2a less than 0. So what this gives me, if we remember from functions, the number line sign scheme, what this gives me is, for this inequality to be valid, x has to lie between the two roots. One root is 0, other root is 2a. So x has to lie between 0 and 2a. So I have found this. And as x approaches 2a, I get infinity. And as x approaches 0, I get y as 0. And it has both plus side and the minus side. So you get two values. So I will try to trace the curve by hand. You just see here how I'm tracing. And then we will check it by the grapher. Okay. This curve is, okay, just a second. All right, doesn't matter. This is y, this is x. Our curve is y square is equal to x cube by 2a minus x. Now, this is 0 and this is, say, 2a. So I'll just draw this line. This is a common problem that comes in entrance exams, this particular function. How to trace it? Now, as x tends to 0, my function is going to 0. And as x approaches 2a from the left, it is going to infinity. So rough calculation, I'm not trying to graph it perfectly, but just it's like tan. Okay. Now, one more thing we can do here to check what will be the tangents at origin. This curve passes through origin 0, 0. You can apply. And we have done tangents through origin, right? So y square into 2a minus x is equal to x cube. So what we get is 2ay square minus xy square is equal to y cube. This is degree 3 term. This is degree 3 term. This is degree 2 term. Okay, good question. Somebody asked, how do we decide whether it is convex or concave? Okay, I will discuss that also. We need to differentiate it and check its sign. Double differentiate and check its sign, or single derivative and check its sign, how it varies. We can, if second derivative is positive, it will be convex. That also I'll do it, no problem. So this is degree 2 term. When degree 2, the lowest degree term, I equate to 0, I get the tangents at origin. So I get y equal to 0 twice. That means it is the x-axis, that is the tangent. So y equal to 0 is a tangent. And why I get it twice, it means that it is tangent for two portions of the curve. So now let us see that. So now, given this, I don't need to find out whether it is convex or concave. Now, when I draw, I will draw like this, that this curve is a tangent to x-axis is the tangent to this curve. So this curve has to be touching the x-axis at 0 and moving away from it. And because the curve lies between 0 and 2a, so naturally this curve, and as x tends to 2a, y value is going to infinity. So this will be the curve. Very good. And the curve is symmetric about the x-axis. Replace y by minus y. The equation doesn't change. So I have my curve here. Done. This is my curve. And we can cross check this. This will be little. Let's see whether we can plot this y square equal to x cube. So y square equal to x cube. We already can find it, divided by x minus 2a, right? Or 2a minus x, sorry. So I will take a as 1. So 2 minus x. Just a second. Why? Yeah. Why it abruptly end? I'm just saying. I'll do 4 minus x, let us say. Yeah. So, and I will draw the line x equal to 4. I will change this equation y equal to x equal to 4. So we got this equation. It is tracing. It is a grapher has an issue. Is it difficult for even the grapher? So what we traced and what we got is the same, right? So this curve is same as the what we draw. So now this is very helpful for us because the question can be find the area bound by this curve and its asymptote. This line is called as the asymptote. Simple question. Question is simple, but because we are not aware of how to trace curves easily, we get scared. But there was no trick. Very simple concepts we have used and trace the curve. Curve is passing through origin. Yes. Equate the lowest degree terms to 0 and you get the tangent, and then find out the domain where y exists for a certain values of x, and then just by simple thought, simple logic, we have drawn the curve. Okay, so this is about tracing the curve. So this is about the regions where the curve does not lie. Okay, next let us consider the next item, asymptotes. Very important concept, very important concept. I think in 10 minutes I'll not be able to cover the full one, but let us try. At least the first portion of the asymptotes I will discuss. The second part, how to find asymptotes for a complex equation, we'll find this. What are asymptotes? In simple words, very simple, not a mathematically correct. It is not mathematically correct, but in simple terms, asymptotes are tangents to the curve at infinity. This definition is of course not mathematically sound, but because infinity is itself not defined, but for a layman understanding, it is very good. That tangents to the curve at infinity is the asymptote. So examples of asymptotes that we have come across. We have very much come across curves like, I'll just plot. You please tell me what is this curve? Anyone?
So e power.
Yes, y equal to e power x. Now, this curve keeps on approaching zero as x tends to minus infinity. All right, as we are going towards minus infinity along the x-axis, the curve tries to touch the x-axis. So this particular line, so tangent at infinity is x-axis. So x-axis is an asymptote. X-axis is an asymptote to the curve y equal to e power x. All right, now let's look at the next one, which we have already dealt with. These curves. What is this curve?
So log.
Y is equal to log x. Now, as x approaches 0, all right, as x approaches 0, y goes to infinity, but this is almost, at infinity, we assume that at infinity it will touch. All right, so this y-axis is an asymptote to y equal to log x, this curve. Similarly, for tan x, the asymptote will be x equal to pi by 2. That will be an asymptote. Okay, so that's the concept of asymptotes. Now let us see this. Now, mathematically sound definition is this: a straight line is called an asymptote to the curve y equal to f of x if the distance from the variable point m on the curve to the straight line to that particular straight line approaches 0 as m recedes to infinity, that m goes to infinity along some branch of the curve. So look at this definition. So m is some variable point. M is some variable point on the curve. And this is this line. What is this line? X-axis is this line. So this is the distance, d. Now m can move along any branch of the curve. Of course, there is one single curve, not like the previous curves where, there are two branches here of this curve. And, earlier curves that we see here also, they are, you can say, two branches of this curve. They are branches of the curve, but here it is a single curve. But anyway, in some direction you go. In this direction, if m moves, the distance keeps increasing. But if in this direction m moves along the curve, the distance approaches 0. As m goes to infinity, as m is moving towards infinity along some branch, this distance between this point m on the curve and that particular straight line under consideration, if the distance goes to 0, if the limiting value of that distance is 0 as m goes to infinity, then that particular line is called as an asymptote. So same here, we take the point m, and distance from y-axis is considered here. This will be d. Now, if m moves away like this, the distance keeps increasing, but if m goes downwards like this, then the distance between m and the y-axis approaches 0. So y-axis becomes the asymptote. But this phenomena will not be valid for x-axis, because for x-axis, distance from the x-axis, I will mark in a different color. Yeah, I will mark this as d2, distance from the x-axis d2. Now this value of d2, it will, as m goes to infinity along the positive x-axis, d2 will also go to infinity, and as m goes to m is moving towards 0 along the x-axis, d2, the value d2 will also keep increasing to infinity. So d2, this particular line will not satisfy, but this line is satisfying that condition. So this is the formal definition. A straight line is called as an asymptote to the curve y equal to f of x if the distance from the variable point m on the curve to the straight line approaches 0 as m recedes to infinity along some branch of the curve. Now, the vertical asymptotes can be classified as 3: vertical, horizontal, and inclined. Vertical asymptote is very simple. Now, a line x equal to a is said to be vertical asymptote if y equal to f of x, for the graph y equal to f of x, if f of x approaches plus or minus infinity as x approaches either x is tending to a, either from the right or from the left, then that is the vertical asymptote. So in the previous question that we did, we find the vertical asymptote like this: as x approaches a plus, here 2a minus, sorry, as x tends to 2a minus, y tends to infinity, it will go to plus infinity because y square goes to infinity. So y will go to both plus infinity and minus infinity. Okay. So put x equal to 0, y goes to infinity. That means that particular, put x equal to a and f of x goes to infinity. Then understand that it is a vertical asymptote. Now look at the horizontal asymptote. The line y equal to b is said to be a horizontal asymptote of the graph of y equal to f of x if either as x tends to infinity, f of x is equal to b, or as x tends to minus infinity, f of x equal to b. So this is, the horizontal asymptote. In the vertical asymptote, x goes to a finite value, y goes to infinite value, f of x goes to infinite value. But in the case of horizontal asymptote, x goes to either minus infinity or plus infinity or minus infinity, and the function approaches a constant value. So here look at the graph of e power x. Yeah, here look at the graph of e power x. So as x approaches minus infinity, limit x tends to minus infinity of e power x is equal to 0. It's a constant. So this is the asymptote. Now we can change it. We can write, if we consider the function as f of x is equal to e power x plus 2, then what happens? Limit x tends to minus infinity, f of x, e power x plus 2 will be equal to 2. Therefore, in this particular case, y equal to 2 is the asymptote. Of f of x is equal to e power x plus 2. So that's how we find the horizontal asymptote. And for inclined asymptote, Very simple. We just need to understand the concept. Sometimes inclined lines are asymptotes to curves, especially for a rectangular hyperbola, like x square plus x square minus y square equal to a square, x square minus y square equal to 4, let's say. You have the asymptotes, we know from hyperbola, the asymptotes are x equal to y and x plus y equal to 0. So how to do that? We will just see. For inclined asymptotes, if the limit x tends to plus infinity, f of x upon x is equal to k1, and limit x tends to infinity, f of x minus k1 times x is equal to b1. Then the straight line y is equal to k1x plus b1 is an inclined right asymptote. Look at this, it is simple. Now this is a line. Let's say this line is an asymptote to a curve. And let's say the curve is something like this. Okay. So this is the curve f of x, y equal to f of x. And this is the line y is equal to k1x plus b1. Okay. This is the slope intercept form of the straight line. So this is b1 and there's this slope. Now f of x upon x, if what is f of x upon x, limit x tends to plus infinity. Okay, now what is happening is, if this line is at as x tends to infinity, this curve is trying to coincide with this line. So it means that, you see, f of x values will almost be equal to k1x plus b1 as x tends to infinity, correct? Because by definition, the distance between the line and the curve is approaching 0. That means the points, they coincide. So as x goes to infinity, the y value will be the same. So what I have done, the y value of the curve, which is f of x, is same as the y value of this straight line as x approaches infinity. Okay. So I've replaced f of x by this. So I get limit x tends to plus infinity, k1 plus b1 upon x. Now as x approaches infinity, this term goes to 0. So I get k1. So limit x tends to infinity, f of x upon x is k1. That means I've found the slope of this line. Slope of this line is limit x tends to infinity, f of x by x. So once I found the slope of this line, now as x tends to infinity, both the equations are y values are same. Therefore, as x tends to infinity, so limit x tends to infinity, the function value and the equation of this line, this should be equal to 0. Okay. That's the idea. So let's, so if this is equal to 0, so at that point, both are equal. That means f of x minus k1x. So if I add b1 on both sides, so that if these two coincide, it also means that f of x minus k1x is equal to b1. So I don't know k1, I don't know b1. So first I find k1, then I find b1. Okay. So because they coincide, the function value of the curve and the function value of the line should match at x tends to infinity. So we get this. So therefore, as limit x tends to infinity, f of x minus k1x should be equal to b1. So then if these two we find, then this line is the inclined right asymptote to the curve. Same we will find as a left asymptote if x tends to minus infinity and we get f of x by x as k2 and f of x minus k2x as b2, then this straight line y is equal to k2x plus b2 is the inclined left asymptote. So we will take some examples of asymptotes tomorrow. Okay. We'll actually solve and take some examples of asymptotes. And after in tomorrow's class, once we do asymptotes, we will see alternative method to find asymptotes in a simple manner. We'll try for some difficult cases. And I have some exercises you can try with whatever I have taught you today. Go through the material which you already have. You go through these and try to find out the asymptotes. And then alternative ways of finding asymptotes also we will discuss. That's it. After that, these points we have already covered, but I'll cover it. Concave nature, convex nature, and point of inflection. Once we discuss this, we are done. Then we dive in tomorrow to finding lengths of plane curves and also finding area bounded by curves. So tomorrow's class will be very important from this point. Today's class was preparing the ground for how to trace curves. Okay, now tomorrow's will be actual integrals, application of integrals. And we also have to discuss conversion from Cartesian curve to polar coordinates, polar equations, and sometimes cylindrical. So we will do that in the next class. All right, thank you.